Let us learn how to construct or how to draw the BODE's plot, which is related to frequency response. Now, the reason why we plot BODE's plot is to comment on the stability of the control system. Normally, what we do is whenever we consider any control system, there are various techniques which are used to predict the stability. So, in BODE's plot, which is a frequency response, we are going to plot two different graphs. One graph is related to the magnitude plot and other graph is related to the phase plot. We all know that whenever we plot a frequency response of any system, we will be plotting two curves. One is the phase plot and another one is the magnitude plot. Now, beyond this, this is what frequency response. Now, beyond this, in BODE's plot, what Bode said, Bode is the name of the person who has given this method. So, what he said is, try to calculate phase margin. Okay, try to calculate the phase margin. And he also gave an instruction to calculate another value which is called as gain margin. Gain margin. Once the magnitude and phase plotting is over, later I will tell you how to plot magnitude and phase margin, phase plot and magnitude plot. But after plotting this phase and magnitude plot, we are going to use a method which I'm going to tell you now, which will allow us to calculate two values. One is phase margin and the other one is gain margin, along with two frequencies. One is gain crossover frequency, gain crossover frequency, gain crossover frequency. In most of the books, phase margin is denoted by capital PM, gain margin is denoted by capital GM, whereas the gain crossover frequency is denoted with omega CP. See, omega CP means it is gain crossover frequency, whereas phase crossover frequency is denoted with omega CG. Okay. So what we are going to do is, once the magnitude and phase plot is done, we are going to use a method which I'm going to tell you now to calculate what is phase margin, what is gain margin, what is gain crossover frequency, and what is phase crossover frequency. Okay. Now, if you look into this diagram which you are able to see on the screen, which I've written here, this is the first condition. This is condition 1. What condition 1 here is, this plot what we have done is actually a magnitude plot. So it is magnitude of G of J omega into H of J omega. And in BODE's plot, one thing you should keep it in mind, that both the magnitude and phase, the plotting of both magnitude and phase should be done in one single graph sheet. Okay, so that is very, very important. Both magnitude and phase plot should be done in a single graph sheet. Now, this graph sheet, for example, this is one entire graph sheet which you are able to see where I plotted magnitude and phase. And this graph sheet, what we use for BODE's plot is always a semi-log graph sheet. Keep that in mind. Semi-log graph sheet. Semi-log graph sheet. I think later when we are plotting this magnitude and phase, you will come to know how the semi-log graph sheet are being used to plot this magnitude and phase in the graph sheet which we consider. Anyway, consider that you have got a magnitude plot like this and a phase plot like this. Okay. So we have a problem, and some problem will be given to you or some question will be given to you where you plot magnitude and phase, and consider that this would be the plot of magnitude that you have got and this is how the phase plot that you have got. So phase means it is this angle of G of J omega into H of J omega. Okay. Now what we need to do is, once the magnitude and phase plot is been obtained, you are going to keep a dot on a place where the magnitude plot crosses 0 dB line. Now, if you see here, this is a 0 dB meeting point of the magnitude plot. Okay, so this is 0 dB line. So normally, the reference line is always 0 dB. Above that, we'll take 20, 40, and then 60, and so on. Whereas below, we take minus 20, minus 40, and minus 60, and so on. Okay, so that is how we try to consider the magnitude plot. Meanwhile, when we take phase plot, we always take a reference point is minus 180 is the reference point. And above can be like, minus 160. If you take 20-20 difference, it can be minus 160, minus 140, and so on. And if you go below, it will be like minus 200, minus 220, and so on. So this is what the phase plot, the plotting that we do. Okay, I think in future, in further section of this particular video, you will be able to learn how to do this magnitude and phase plot. There you will see whatever I'm saying. So this is in degrees. Keep that in mind. This is in degrees. Now, always for a phase plot, we take a reference line which is minus 180 degree. Whereas a magnitude plot, we always take a reference line which is a 0 dB line. So this is 0 dB. Okay. So at this point, it is 0 dB. Now, what we do is a magnitude plot crosses 0 dB line. We have put a dot here. Okay. Similarly, a phase plot will cross minus 180 degree line. So we'll put a dot there. Okay. So we'll put a dot there. Now, we will try to draw a line. Okay. We'll try to draw a line which is vertically, from this point, we draw a line. Okay. That point, we draw a line which should cross both phase plot and the frequency omega. Okay. So we draw a line from 0 dB point vertically, which crosses the phase plot, minus 180 degree line, and also the frequency. Okay. Similarly, we'll try to draw a same sort of line which is from minus 180 degree point. It is the point where the phase plot has crossed minus 180. We take a horizontal vertical line which we draw, which crosses frequency, and also upwards, which should cross the magnitude plot. Which should cross a magnitude plot. Okay. So this is how we try to, mark two different vertical dotted lines, which is from 0 dB to the bottom, where it should cross phase plot and minus 180 degree line, and also touch the frequency line. Similarly, we'll take phase plot where it teaches minus 180 and draw a vertical line which crosses the magnitude plot and 0 dB line, and also we try to draw the line downwards which crosses the frequency line. Now what we are going to do here is, once we do this, we are now going to calculate what is phase margin and gain margin. Now, a line drawn at 0 dB, which is 0 dB, vertical line which you have drawn, the distance between the phase plot and minus 180 degree will give you the phase margin. It means that this. So we'll give you the phase margin. It means this distance which I'm saying. This is a distance, a curve, the distance between the curve, phase curve and minus 180 degree line. This gives you phase margin. Similarly, you have drawn a line from minus 180 degree point upwards where it crosses the magnitude plot and the 0 dB line. So the distance between that 0 dB line and this magnitude plot is actually gain margin. This is gain margin. Fine. Now, the line what you have drawn which gave you phase margin is actually frequency. Now, we need to know two different frequencies here. See, at the bottom we have two frequencies which touches these two vertical lines. The frequency for which you got phase margin is actually gain crossover frequency. Okay, this is gain crossover frequency. You might get confused. See, I have written CP, so you might think it is phase crossover. No. Why I'm using this? Because in most of the books which you refer, the gain crossover frequency is referred as omega CP, whereas phase crossover frequency is referred as omega TG. Okay, so you got phase margin because of gain crossover frequency, and you got gain margin where a vertical line is drawn from minus 180 degree, which you have. This is called as omega CG, and we call this as phase crossover frequency. Okay. Now, if you see here, this type of curve or this condition one, which I said, we are speaking about condition one. So what is a condition one is when omega CP is less than omega CG, when omega CP is less than omega CG, we will be getting phase margin, above minus 180 degree line. Now, if you see your phase margin, this is minus 180 degree line, and you got phase margin above 180 degree, right? Minus 180 degree. Similarly, you will get gain margin, which is below 0. Gain margin, which you get below. Now, this is 0 dB line. If you see here, this is 0 dB line, and below 0 dB is what you got the gain margin, right? The magnitude and 0 dB is below 0 dB line, this distance. So, therefore, So let me draw it. This distance is actually gain margin, and this distance is actually phase margin. Therefore, what we comment here is, once we got phase margin above minus 180 degree, then such phase margin is actually considered to be positive. Keep that in mind. If the phase margin is obtained above minus 180 degree, then such phase margin is considered to be a positive phase margin. Similarly, when you get gain margin which is below 0 dB line, then such gain margin is considered to be positive. Okay. If you get below 0 dB, gain margin is positive. Above minus 180 degree, phase margin is positive. And if you get a condition in this way where both are positive, both phase margin and gain margin are positive, then such system is considered to be stable. So this is the condition for stable system. This is what Bode says. If you get phase margin and gain margin both positive, then this such condition or such system is considered to be a stable system. I hope you got this, right? Now let us go to the next condition. Now this is condition 2. Let me say this is condition 2. This is condition 2. Now let me go with condition 2 and tell you what is that we get. Similarly, we have a phase meeting at minus 180 degree and we have gain meeting at 0 dB line. So we'll draw, as per for the previous discussion, we'll draw a vertical line from minus 180 degree upwards, which crosses the the magnitude plot. Okay, and should also cross the phase plot. Similarly, we have a 0 dB line here, or 0 dB point where the magnitude has met. So we'll draw a vertical line. Okay, we'll draw a vertical line which meets that point and also crosses the magnitude plot. Okay. Now, if you see here, means we have drawn two different vertical lines from minus 180 degree point, both upwards and downwards. Upwards, it crosses the magnitude plot along with 0 dB line, and downwards, it crosses the frequency. Okay, so this is the frequency point which I'm saying. So now, these two are the frequency points. This is one point and this is second point. Okay. So now, after drawing these two lines, now what we need to do is we need to identify what is phase margin and gain margin. Okay. Now, as this vertically drawn and you see a magnitude curve is this and this is 0 dB line. So the difference between magnitude and 0 dB line is this. This is the distance. Now this is considered to be our gain margin. Similarly here, a 0 dB line is drawn downwards where minus 180 degree and phase plot is crossing here. So this distance is now considered to be phase. So here, this distance is gain margin, whereas this distance is phase margin. And we all know, like I told you earlier, the gain margin is obtained due to the phase crossover frequency, which is omega g, whereas the phase margin is obtained due to gain crossover frequency. Okay, so this is phase crossover, and this is gain crossover. Okay. Now, if you carefully observe here, how omega Cp, earlier it was less than omega Cg, now omega Cp is greater than omega Cg. This is condition 2. Meanwhile, you see that for this condition, the phase margin, what you got is below minus 180 degree line, whereas gain margin, what you got is above 0 dB line. Okay. Now, what do we comment here is, if the phase margin is below minus 180, then the phase margin is considered to be negative. Whereas if the gain margin is above 0 dB line, then the gain margin is considered to be negative. Keep that in mind. If the phase margin is below minus 180, it is negative, and gain margin above 0 dB, then it is negative. Then this condition is considered to be unstable. If both gain margin and phase margin are both negative, then the condition is called as unstable. Fine. So this is unstable. So any system, if you get a curve like this, then such system is considered to be unstable. And the previous condition which we discussed, any system which generates such curve, then that condition to be, which we saw earlier, was stable. Now we have one more condition which we normally see, which is called as condition 3. Now, what is condition 3 here is, you see that the magnitude meets at 0 dB and the phase meets at minus 180. They form a same vertical line. See, they form a same vertical line. They both meet at the same single point frequency. So this condition says that omega Cp and omega Cg are equal. See, this is omega Cp and the same point is also omega Cg. Therefore, they both are equal. So here we are not able to identify what is gain margin and what is phase margin. We are not able to calculate because both the corner frequencies are equal. Both the crossover frequencies are equal. So therefore, that system, what we call it as marginally stable. Marginally stable. So this is condition 3. Okay, so which is a condition for marginally stable. There might be one more condition 4. Let me tell you that what is that. The condition 4. Sometimes what happens here is, sometimes, the gain, okay, let me take out everything and try to tell you what I'm saying. So here, I'll just erase this part. And I'll also erase the phase plot for condition 4 and tell you what it is, what I'm saying here. Now think that you got a phase plot in this way and it is going like this way and it is meeting minus 180 here. Fine. Think that you have got a phase plot in this way. Whatever I've drawn, it is coming this direction, okay, going late and meeting the minus 180 line little bit late, like this. Now think you got a phase plot like this. Now what I'll do is I'll draw a vertical line for you, like this is a 0 dB line if you see here. So I'll draw a vertical line from 0 dB crossing phase plot and meeting the frequency. Okay. Now you don't have the same frequency now. Let me erase. This is not the condition which I'm saying now. So the earlier discussion what we did for marginally stable, now it is not marginally stable because you don't have omega Cp and omega Cg in the same place. Okay. Now as 0 dB line is there, this will give you what? This will give me a distance between minus 180 and phase curve. So I can easily say that whatever I got here is phase margin, right? Phase curve between phase curve and minus 180 degree. So this is phase margin. Now my system is meeting minus 180, phase plot meeting minus 180 at this point. Okay. Now what I'll draw a line from this point. Okay. This is what we have got here. A 0, I've drawn minus 180 degree point which where the phase met, and I've drawn a vertical line which is crossing the magnitude plot. But if you see here, unfortunately, I'm able to get phase margin. But if you see here, there is no gain margin at all because my minus 180 degree line is not at all crossing the magnitude plot, right? So what we have here, whatever we have here is omega phase margin is due to gain crossover frequency, which is omega Cp, and whatever we have here is the phase crossover frequency, which is omega Cg. Now, what is the condition here is we are not having any omega Cg which can define gain margin. This is the condition because we have omega Cg in the diagram, right? We have marked omega Cg which is related to minus 190 degree point on the phase plot. But unfortunately, when we see vertically upwards, we don't have any magnitude plot crossing this line. So therefore, there is no gain margin at all. We don't have gain margin at all. So therefore, we are not having any omega Cg which can define gain margin. So we consider, in this case, gain margin to be infinity. Keep that in mind. When we don't have any omega Cg which can define gain margin, then we consider such gain margin to be of infinite value. Okay. And if you see towards phase margin, as it is above minus 180 degree, we normally consider phase margin to be positive. I hope you got it. We have gain margin, it is infinity because no omega Cg can define gain margin. But phase margin is easily obtained in this curve, where phase margin is above minus 180 degree. And if it is minus 180 degree above, then we consider phase margin to be positive. Then in such case, we call the system is stable. Okay, because practically gain margin should be positive. But what is the positive value? Gain margin should be greater than 1. Gain margin should be greater than 1. Less than 1 gain margin is also unstable condition. Though the gain margin is positive, but positive value should be greater than 1. Keep that in mind. Less than 1 is also unstable condition. So in condition 4, we were able to get a gain margin to be infinite and phase margin to be positive. Therefore, as infinite is a positive value, therefore we consider such system to be stable. Okay, so this is what BODE's plot initial knowledge that you need to keep in mind before learning BODE's plot and commenting on stability. You have to keep this knowledge first. Okay, this initial knowledge is very, very important for you to work on BODE's plot. Anyway, in this video, I'm going to stop here. So kindly watch this video once again if you are still confused. In next video, we'll see how to work on BODE's plot by considering some good examples. Thank you.